Okay, so welcome back to this next video in which we are discussing subspaces of vector spaces. Okay, so we've now seen what the definition of a subspace of a vector space is. Okay, so we've seen that fundamentally a subspace, capital W, of a vector space, capital V, over the field, capital F, is going to start off as just a subset of the vectors within capital V. Okay, but it needs to be a special subset of the vectors in capital V, because it needs to be a subset which, if you have the inherited addition and scalar multiplication laws on that subset from the larger vector space capital V, it needs to be the case that this set W with these inherited composition laws on it is a vector space in its own right. Okay, so what we're now going to look at is what criteria then does a subset of a vector space have to obey in order for it to be the case that it is a subspace? Because you can summarize it down to just having to check 3 criteria. So I'm going to state those 3 criteria that you have to check, and then what we're going to do is explore the reason that these 3 criteria being true actually means that the subset will indeed be a subspace. Okay, so if you've got then a subset of vectors of the vector space capital V, and you want to check whether this subset is actually a subspace, these are the criteria then that you have to check. So criterion number 1, okay, says that for all 2 vectors that are in your subset, okay, so we'll say for all little w and little w bar here, which are elements of your subset capital W, it must be the case that when you add them together with the inherited composition law, so w plus w bar here, whatever that answer is, it must also be in the subset capital W. So basically the subset capital W must be closed under the inherited addition law. Okay, so all of the answers in this inherited addition composition table must be back within the subset capital W. Okay, you have to make sure that there's no elements in this inherited addition law here that are outside of the subset capital W, okay, that are in this portion of V, because if you have any answers here, then that's not actually going to be an abelian group of W, basically, okay, because then it won't be closed. So for this addition composition table to be an abelian group for this subset W, we must have it the case that all of the answers in this addition composition table are within the subset capital W itself. Okay, so that's criterion number 1 that you have to check. Criterion number 2 then says that for all elements of the field, so for all little c is an element of the field capital F, and for all vectors in the vector, in the subset at the moment, we don't know that it's a subspace yet. Okay, so for all c is an element of the field and for all little w is an element of capital W, it must be the case that c times w is also an element of your subset W. Okay, so what this is saying basically is that scalar multiplication must be closed. Okay, so when you scalar multiply any of the vectors that are in this subset W by any of the elements of the field, all of the answers that you get must again be in the subset W. So that's basically saying that for this scalar multiplication table here, all of the entries must be in W, basically. You can't again have any vectors as your answers which are outside of W. Okay, so it must be closed under scalar multiplication by elements of the field. And finally, the 3rd criterion then is that the 0 vector from the vector space capital V over the field F must be an element of your subset W. Okay, so the additive identity within your entire vector space must be in your subset W. Okay, and that's so that this inherited addition law that's on the subset W is actually going to have an identity element. Okay, so that's the final criterion. Okay, so what I want to do is go over the reason then now that if you have a subset W, which is a subset of your vector space capital V over the field F, and it obeys these 3 criteria here, why is it then the case that this subset is indeed a subspace? Okay, specifically, why is it the case that that subset with the inherited addition and scalar multiplication laws on it is actually a vector space in its own right? So we want to make sure that these composition tables here are going to obey the criteria of vector spaces. So let's firstly start off with the inherited addition one here. So we know that the inherited addition composition table here must be an abelian group. Okay, so W, this subset with this inherited addition composition table, must be an abelian group. Okay, so there are 5 axioms for being an abelian group. The 4 of normal group theory, and then the 5th one will be the commutative property. Okay, so we need to check that these are all going to be true, so that will be our first job here. Okay, and all that we've got is these ones to be working on. Okay, so axiom number 1 then of an abelian group is that it needs to be closed. Okay, and that's exactly what we've got here. So again, for W with this inherited composition of addition on it, to be an abelian group, it needs to be closed. So it needs to be the case that if you take any 2 vectors, W and W bar, from capital W, and you then add them together with this inherited composition law, it must then be another element of our subset capital W. Okay, so all of the answers in this addition composition table must be in the subset W itself. So that's really, really important, and it's not trivial at all. Okay, with many subsets, if you just take this inherited or restricted addition composition table from the larger vector space capital V, you'll end up with answers in this composition table that won't be in the subset W, but will be in the portion of V that is outside of W, and you don't want that at all. You want all of the answers in this restricted addition composition table to be back within the subset W. Okay, and of course criterion number 1 is going to make sure of that. So if we do have criterion number 1 here being true, then indeed our restricted addition composition table is going to be closed. Okay, so that's good. Okay, axiom number 2 then of group theory is associativity. Okay, so this says that take any free vectors, so W, W bar, and W double bar, let's say, which are all elements of our subset capital W, it must be the case that if you add all 3 of them together, that there's only one answer, so it shouldn't matter where we put the brackets. So we can either put the brackets around W plus W bar, or we can put the brackets around W bar plus W double bar. Okay, and the answer must be the same no matter what W is, no matter what W bar is, and no matter what W double bar is. Okay, so associativity must be true. Now, we don't actually need to worry about associativity being true, because associativity has to be true in the larger vector space. Okay, so the entire addition composition law here obeys associativity. Okay, it's the case that if you take any 3 vectors from the entire vector space and want to add all 3 of them together, that it doesn't matter where you put the brackets. Okay, there is one and only one answer. Okay, all of these 3 vectors here are from the larger vector space capital V. So when we add the 3 of them together with the restricted composition table, then it must still be the case that it doesn't matter where you put the brackets, because of the fact that really when we create this inherited addition law on the subset, it is just a restriction down of the larger addition law. Okay, so if it was the case that this wasn't true, then it wouldn't have been true in the larger addition law either, and therefore it would contradict the larger vector space capital V actually being a vector space. Okay, so we get associativity for free, as indeed we always did when we had subgroups of groups. Okay, so we don't need to worry about associativity. Okay, axiom number 3 is that we must have an identity element. Well, criterion number 3 here says that the additive identity from our larger vector space capital V, which is the 0 vector, must be in our subset capital W. Okay, so provided criterion number 3 is true, we indeed do have the identity element from our larger vector space in our subset. Okay, so we will have that criterion being true. Okay, so that's fine. Okay, then axiom number 4 concerns additive inverses. I think I'll come back to axiom number 4, and I'll firstly do axiom number 5. Okay, and I'll go over the page to do this. Okay, so we'll come back to axiom number 4 because that's the more complicated one. That's the one that it isn't immediately obvious why that's true. Okay, so we'll go to axiom number 5 first. So axiom number 5 is commutativity. Okay, so we need to make sure that, whatever two vectors you take, w and, not like that, w and w bar that you take from the vector subset, capital W, that when you add them together, it's the same if you do it the other way around. So w plus w bar must be the same as w bar plus w. Okay, so we want our inherited addition composition table to be commutative. Now, why is that always going to be true? Well, it's because the addition composition table on the larger vector space was commutative. It was an abelian operation. Okay, so again, the same argument applies for associativity. We are just restricting down our attention. We're just taking a little portion of that composition table that we had on the larger vector space, capital V. Okay, so effectively we've just shrunk this down, we've chopped a bit off like that. Okay, now if commutativity was true on the entire thing, if it was true that this entire thing was symmetric down the diagonal line, which is indeed what commutativity means, then when we just chop off a huge bit like so and have a restricted version of it, that's still going to be symmetric down the diagonal line. It's still going to be commutative. Okay, so that's why commutativity is obeyed by this inherited addition law. Okay, so that one's nice and easy. Now let's go back to axiom number 4, because that's the most difficult one, and that's the one that it's not immediately obvious that that's going to be true. Okay, because we don't have it written in these three criteria here. Where does it say that there must be additive inverses present within this subset of vectors, capital W? Well, in fact, it's contained in this second one, the one that we haven't used yet. Okay, and the reason is, okay, that if we are insisting that all scalar multiples of a vector W are actually going to be present within this subset, we're actually going to end up with the additive inverse being in there anyway. Okay, so let me explain why. So what we want to prove, axiom number 4, is that whatever element you take of this subset, so whatever little w you take from the subset capital W, it must be the case that its additive inverse, negative W, must always be an element of capital W as well. So how are we going to prove that? Well, the first thing that I want to show you is that the additive inverse of a vector W, so the additive inverse of W, negative W, is actually equal to -1 in the field times W. Now that might look ridiculously trivial, but we do need to show that at some point. Okay, now is our moment. Okay, so the first challenge that I want to address is trying to make you realize that that isn't completely trivial. Okay, because these two things are not the same thing. This, on this side, the left-hand side here, negative W, that just means the additive inverse for W in the vector space capital V. Okay, it means the vector that will add to W in the vector space addition to give the 0 vector back again. Okay, so W plus negative W will equal the 0 vector. Okay, where all that addition there is addition in the vector space addition. This side, what does this mean? This means take the field element -1. Now, what is meant by the field element -1? Well, of course, what we know is that 1 is an element of the field. 1 is the multiplicative identity in the field. Now, all elements in the field have an additive inverse, so -1 means the additive inverse of the multiplicative identity in the field capital F. Okay, now that's an element of the field. We can scalar multiply any element of the field with a vector. Okay, and that's indeed what I'm doing here. So what I want to prove is that if I scalar multiply the additive inverse of the multiplicative identity in the field by my vector, I end up with the additive inverse of my vector in the vector space. So that's not, these two sides of the equation are not the same thing. We do need to prove that they are going to actually equal one another. Okay, and I realise that what I've said doesn't sound as though it makes sense. Okay, it's not absolutely obvious that they're the same thing. They are going to be the same thing because vector spaces are so beautiful. Okay, but these do mean doing different things, and it's just because of how beautiful vector space is that these two things are going to end up being the same thing. Okay, so I want to prove then that if I take -1 and multiply it by vector w, I end up with the additive inverse of that vector w. So what I want to prove basically is that if I take w and add it to -1 times w, that I end up with the 0 vector. That's what it means to say that this thing here is the additive inverse of w. So I need to show this. Now how am I going to show this? Well, I'm going to use the axioms of a vector space, and understand at the moment I'm doing this in the larger vector space capital V. After all, if w is an element of the subset capital W, then it's also an element of the larger vector space capital V. Okay, so the way I can do this is I can put in an extra thing here. I can put in 1 there. Okay, so I can imagine that w here is just 1 times w. Okay, and that's a perfectly valid thing to do, okay, because we know that the multiplicative identity of the field multiplies by any of the elements of the vector space just to give that same vector back again. So now what I've got is that this side, this left-hand side here, goes to 1 times w plus -1 times w. So I'm trying to work out what this is, but now I can use my distributive law. Okay, part 2 distributivity, and I'll just remind you of what that says. So part 2 distributivity here concerns when you have 2 elements of the field and 1 vector, and it says that if you add 2 elements of the field together and then scalar multiply that element of the field by a vector, then it's the same as if you firstly scalar multiply the vector by each of those elements of the field and then add them together. Okay, I'm going to use that in reverse. I'm going to say that this is now the same thing as 1 plus -1, where this addition is now done in the field, scalar multiplied by w. But what is 1 plus -1 in the field? Well, -1 is the additive inverse of 1, so they will add together to give 0 in the field, the additive identity in the field. Now 0 will multiply by any vector. It's something that we proved in the video on the definition of a vector space, that 0 will multiply by any vector, scalar multiply by any vector to give the 0 vector. So understand that this 0 is not the same as this 0. This is 0 in the field, this is 0 in the vector space, okay? It does look confusing, but of course you will get used to it, okay? So what we have now succeeded in proving then is that w plus -1 times w is equal to the 0 vector, and that then means that -w must indeed equal the additive inverse of w, i.e. it is, sorry, -1 times w must indeed equal -w. It is the additive inverse of w. Okay, right, so that's how we're in fact going to go about proving that if those 3 criteria were true, we actually do have additive inverses, okay, because criteria number 2 that our subset needed to obey in order to be a subspace was that all scalar multiples of the vector, any vector in the subset, have to be also within the subset. Okay, so if I take any vector any vector w in the subset capital W, all scalar multiples of that have to also be in the set capital W. In particular, -1 times w must be an element of capital W, and -1 times w I've now shown is the same as the additive inverse of w. So that means that the additive inverse of w must be in w. So indeed we have now successfully shown that with this inherited addition law on it, the subset will be an abelian group under addition. Okay, if it obeys those 3 criteria. Okay, what I now want to show you is that it will also actually be a subspace. So we need to now turn our attention to scalar multiplication and make sure that all the axioms of scalar multiplication are going to work. So let me firstly just redraw out a picture of the reduced scalar multiplication law. So we still have all the elements of the field here. So all the elements of the field are going to be down here. They're all going to be given a row that will correspond to them. Okay, so here are all the elements of the field. Sorry for knocking it there. Okay, and then up here now, we're not going to have the entire vector space, of course. Now we're just going to have our subset capital W, okay, and we want to prove that this restricted scalar multiplication law is actually going to obey the axioms that it needs to obey in order for this subset capital W to be considered a vector space. Okay, so what are those axioms? So axiom number 1 then was that all of the answers in this scalar multiplication table need to be back within the vector space capital W. So for all C is an element of the field capital F, and for all W is an element of capital W, it must be the case that C times W is an element of capital W, so that all the answers here are in the subset capital W, not outside of capital W. And again, that's not totally trivial. Okay, if you just take an arbitrary subset of a vector space capital V, it's unlikely that that will actually be true. Okay, so this subset needs to be very special so that this inherited or restricted scalar multiplication law actually is closed, so that when you take any element of the subset and scalar multiply it by any element of the field, you'll get an element that's back within that subset. And of course that is just criterion number 2 that we insisted was going to be true on this subset. So that one we don't need any effort to prove that if those 3 criteria are true, that one is going to be true. Okay, so indeed all the answers here are going to be back within our subset capital W if those 3 criteria about the subset are true, because indeed this is just a replica of one of them. Okay, right, so now let's check the other axioms then that scalar multiplication needs to obey. Axiom number 2 next, which is associativity. Okay, so this says take 2 elements of the field, so for all C1 and C2 are elements of the field, okay, and for all little w is an element of capital W, it must be the case that if we look at C1 times C2 times W, that it's the same as if we firstly multiply C1 and C2 together in the field and then scalar multiply that by W. Okay, so these 2 things must be identically equal to one another. Okay, now why is that going to be true? Well, again, that's going to be true because of the fact that this is just a restricted portion of the larger scalar multiplication table that we had on the entire vector space capital V. Okay, so both of these elements of the field, they're just elements of the field, so they were there in the larger vector space scalar multiplication table, and this little w, this is also an element of capital V. Okay, so this has to be true because it was true in the larger scalar multiplication table. Okay, and this is just a restricted part of that scalar multiplication table. So if this was not true in this smaller scalar multiplication table, it wouldn't have been true when this smaller scalar multiplication table was part of the larger scalar multiplication table, and therefore our larger vector space couldn't have been a vector space. Okay, so we know our initial assumption was that it was a vector space, so this must be true basically. So again, this one just comes very naturally because of the fact that it is just a restriction of that scalar multiplication on the larger vector space. Okay, next up, axiom number 3. Axiom number 3, remember, concerns the multiplicative identity of our field, and it says that the multiplicative identity 1 must scalar multiply all vectors of the vector space, and I must call that W, not V, okay, to give W for all little w is an element of capital W. So 1 times any vector in the vector, in the subset capital W must give that same vector back again. Okay, well, why is that going to be true? Well, again, it's just a restriction of the scalar multiplication on the larger vector space. So if we think about the row corresponding to 1, this is just a small portion of the row corresponding to 1 in the larger scalar multiplication table. In the larger scalar multiplication table, we just had more columns. This went on and covered the entire vector space capital V. I might even draw this in, so it might have gone all the way over to there previously. Okay, now we've just chopped off the rest of that, but we haven't changed this portion of the row corresponding to 1. This is still exactly as it was in the larger row corresponding to 1 in the larger scalar multiplication table. So indeed it will still send all of the elements of this subset onto themselves, all of those vectors. So indeed, axiom number 3 will be satisfied because of that. Okay, and then axiom number 4, the distributivities, and again these are just going to be true because of the fact that it's a restricted version of the larger scalar multiplication table. So part 1 distributivity says that for all C that you can possibly pick from the field capital F, okay, and for all two vectors that you can pick from the subset, so W and W bar, which you can pick from the subset, it must be the case that C times the two vectors added together, W plus W bar, must equal C times W plus C times W bar. Okay, so scalar multiplication must distribute over addition of vectors in the vector space. Okay, right. So again, this is going to be true because it was true in the larger scalar multiplication table for the entire vector space. So these are vectors from the larger vector space. Okay, so if we're now working in the larger vector space, this statement was true, okay, but all of these things are now relevant in our reduced scalar multiplication table. They still mean something in our reduced scalar multiplication table, and this is just a replica of the larger one, so indeed this is going to be true as well. Indeed, if it wasn't true in the reduced scalar multiplication table, then it wouldn't have been true when this reduced scalar multiplication table was part of the larger scalar multiplication table. So that has to be true as well. And it's the same for the other distributivity as well. So part 2 here says that for all two elements of the field you pick, C1 and C2 are elements of the field, and for all vectors you pick, little w is an element of capital W, it must be the case that if I take C1 plus C2 and multiply that by little w, it must be the same as if I firstly multiply C1 by W and then add it to C2 times W, where this addition is done in the vector space and this addition is done in the field. Okay. Now again, this is going to hold true because little w is an element of the larger vector space capital V. Okay, you can do this in the larger vector space capital V, but all of these things, all of these objects that you've got here, C1 times W, C2 times W, C1 plus C2 times W, they're all elements of the smaller set capital W. Okay, so all of this has meaning in the smaller subset capital W, so indeed this is still true in the smaller subset capital W. Okay, because of the fact that our composition laws in the smaller subset capital W are just the restricted composition laws from the larger vector space. Okay, so we have now seen then that if we have a subset capital W which obeys those three criteria, that it's closed under addition, it's closed under scalar multiplication, and it contains the additive identity, the zero vector, from our larger vector space capital V, then it will be a subspace. Okay, it will be a very special subset because with the inherited or restricted composition laws from the larger vector space, it itself obeys the axioms of being a vector space, and that's what we call a subspace of a vector space. Okay, so we'll call it there for this video, and in the next video what we'll do is we'll do an example of this. So we'll firstly have a look at subspaces that are always subspaces no matter what vector space you're working in. Okay, so they're called the two trivial subspaces, and then what we'll do is have a look at the subspaces of the vector space R3.